Good evening, ladies and gentlemen. Can anybody hear me? See me?
Yes.
All right. Welcome to this is the last full week of October, huh? Okay, we just have one section tonight, 4.1. We are going to start a brand new chapter, and we're going to learn how to solve what are called systems of two linear equations and two unknowns. Today, we're going to focus on one technique called the graphing method. And as the name suggests, we're going to have to graph. And you're really going to need graphing paper in order to be successful, ladies and gentlemen, in this section. So please do get your hands on some graphing paper to do section 4.1. All right, I will make available the chapter 4 quiz on Wednesday, and also the chapter 3 and 4 exam on Wednesday. I will make that available, and I'll specify the due dates for those things. But any questions before we get going here? Section 4.1. All right, so let's dive right in to section 4.1. Okay, so systems of two linear equations and two unknowns. Right, in general, ladies and gentlemen, these systems look this way. Here we have a system of two linear equations and two unknowns. These are linear equations because x and y are to the first power in both equations. And we're going to show you how to solve these systems of two linear equations and two unknowns. The solution or solutions to such a system is an ordered pair that satisfies both equations simultaneously. So in order to be a solution to this entire system, our ordered pair solution needs to satisfy both these equations simultaneously. It must be a solution to the first equation and the second equation. If it fails to be a solution to just one of the equations, then it's not a solution to the system. Okay. These systems have either one solution one unique ordered pair solution, in which case these systems are often referred to as consistent systems. Or such a linear system of two equations and two unknowns has no solution. Such a system as this is referred to as an inconsistent system. Or there's one other scenario. There could be an infinite number of solutions. Such a system is called a dependent system. Methods of solution. There's three main methods of solution that we will show you before the week is over. First method is called the graphing method. We're going to show you that today. Second method is referred to as the addition or the elimination method. And the third method is called the substitution method. Today, we're going to focus on the graphing method. And because we need to be accurate in our graphs, you need to use graphing paper. That's a requirement. So in order for this graphing method to work, it is imperative that we get our hands on some graphing paper to do section 4.1. Okay. Any questions so far about this page? All right. Well, let's see if we can solve a system or two using the graphing method. Well, tell you what, before we do that, let me ask ourselves a question. Is -2,5 a solution of the following system? X plus y equals 3, 3x plus 4y equals 2. Well, to be a solution to this system, this ordered pair has to satisfy both of these equations. That's to say, I replace the x coordinate with -2, the x variable with the x coordinate -2, and the y variable with 5. So is -2,5 a solution to the first equation? So -2 goes in for x, 5 goes in for y. Is this a solution? Does it satisfy the first equation? And the answer is yes. Is -2,5 a solution to the second equation? That means if I replace x with -2, replace y with +5, is the second equation satisfied? This is -6 plus 20 is equal to 26, and that's not equal to 2. So the answer is no. So since -2,5 is not a solution to the second equation, it is not a solution to the entire system of two equations and two unknowns. It's not a solution.
Can you slide that up?
What's that? No. So it doesn't
Thank you.
satisfy both equations. So -2,5 fails to be a solution to this system because it is not a solution to the second equation. All right, it has to be a solution to both equations in order for it to be a solution All right, any other questions about this right here? So we verified that -2.5 is not a solution to that system of two linear equations and two unknowns. Let's try another ordered pair. Is 10 -7 a solution to the system of two linear equations and two unknowns? So is it a solution to x plus y equals 3? 3x plus 4y equals 2. Replace x with 10. Replace y with -7. Does the ordered pair satisfy the first equation? The answer is yes. So 10 -7 is a solution to x plus y equals 3. Does it satisfy the second equation? Replacing x with 10, y with -7. Is the second equation satisfied? 30 plus a -28. Is that equal to 2? And the answer is yes. So 10 -7 is a solution to the second equation. So is it a solution to the entire system? What do you think? Yes or no?
Yeah.
Yes. So it is a solution to the entire system because it satisfies both equations simultaneously. Well, that's great. We now know how to verify whether an ordered pair is a solution to a system, but how are we going to find the solution now? Well, there's three methods, like I said, for solving these systems: the graphing method and a couple of algebraic methods, the addition method and the substitution method. We're just going to concentrate on the graphing method today. Okay. All right, do we all have this accounted for here? Okay. Well, let's now begin to use this graphing method to solve these systems. So the instructions now are going to shift to the word solve. And the first system we'll look at is x plus y equal to 4 and x minus y is equal to 2. So we're going to try to solve the system of two linear equations and two unknowns by using the graphing method. All right, so what we're going to have to do is we're going to have to graph both these equations in the xy plane. So we're going to have to graph x plus y equals 4. And we're also going to have to graph the other one. X minus y equals 2. So how do we graph this linear equation? Well, we've seen that there's many ways to graph a linear equation. You could use the table method, the xy intercept method, put this in the slope intercept form and graph it that way. Okay, I'm going to use the xy intercept method. So how do I find an x-intercept? Do we remember? How do we find an x-intercept? What do I always set equal to 0 to find an x-intercept?
Oh, wow.
I,
It was my birthday. She took me out because she understood that.
So we set y equal to 0. Therefore, you take 0, substitute it in for the y variable. And you get x equals 4. So my x-intercept is going to be 4, 0. Now the y-intercept. What do we set equal to 0 to find the y-intercept always? we set the other variable, x equal to 0. Take 0, substitute in for x, and your equation then becomes this. So your y-intercept is 0, 4. All right, so we know our x-intercept is 4, 0, and our y-intercept is 0, 4. So let's take a piece of graphing paper and plot those points and graph that first equation in that system. So we take ourselves a piece of graphing paper here, ladies and gentlemen. I'm going to plot the points 4, 0. There's the x-intercept, and then I plot the point 0, 4. There's the y-intercept. Take a ruler and put a line, a neat line through these points. Make sure you go right through the center of the points too, because neatness is going to be of paramount importance in order for this solution method to work. So that would be the graph of that first linear equation in our system. Now this is optional, you don't have to do this, but along this line, I like to put the equation that generated it so I know from whence it came. So I'm going to put the equation that generated that line. Now we're going to graph the second equation in the same XY plane. To graph this one, again, I will make use of the XY intercept method. Feel free to use any other method to graph it. You don't have to use the XY intercept method to graph this. There's many other ways. You can use the table method. You can put this in the slope intercept form and graph it that way. Well, ladies and gentlemen, I'm going to use the XY intercept method. So to find the x-intercept of the second linear equation, I once again set y equal to 0. Take 0, substitute in for the y variable, and therefore x is equal to 2. Hence my x-intercept is 2, 0. Finding the y-intercept involves me setting x equal to 0. Take 0, substitute in for the x variable. Hence I got negative y is equal to 2, which implies that y is equal to negative 2. So my y-intercept is 0, negative 2. Any questions how we found the x and y-intercepts for both these linear equations? All right. I'm now going to graph the second line in the same XY plane that I graphed the first one. I'm going to do so by plotting the x-intercept of 2, 0. And then I plot the y-intercept, which is 0, negative 2. Take a ruler, put a line through these points. And I have the graph of that second linear equation in that system. And along this line, I'm going to put the equation that generated it, x minus y equals 2. So that's the graph of both those lines. Any questions? All right, no questions how we graph those linear equations. Now, can we read off this point of intersection? That's why neatness is important here, ladies and gentlemen. We got to be able to read off this point of intersection. What's its ordered pair address?
3, 1.
3, 1. Ladies and gentlemen, what's the significance of that point 3, 1? What do you think the significance of that point is? 3, 1 is the only point of intersection between those two lines. What do you think the significance of that point 3, 1 is in the scope of what we're doing here?
Satisfies the solution to both.
It's what?
It satisfies the solution for both problems.
You are correct. Ladies and gentlemen, therefore we have solved this system graphically. The solution to this system of two linear equations and two unknowns is the ordered pair 3, 1. Okay. 3, 1 is the only solution to that system of two linear equations and two unknowns. It's the only point of intersection between these lines. So this should be a solution, which means it should satisfy what? Both equations. So what I want you to do is I want you to take this ordered pair 3-1, and I want you to demonstrate on your paper right now that it satisfies both of these equations. So everybody do that right now. Verify that 3-1 is a solution to both equations.
I can't hear you.
Okay, what we're doing is we're verifying that 3-1 is a solution to the system of two equations and two unknowns. So
Okay, thank you.
I want you to do that. Verify that 3-1 satisfies the system.
Thank you.
So, ladies and gentlemen, we have verified that 3-1 is a solution to this system because it satisfies both equations, correct? Does that make sense?
Yes.
And you can clearly see that it is the only solution to this system because it's the only point of intersection that's shared by the graphs of both those linear equations in that system. So what kind of a system would we call this? A consistent system, inconsistent, or a dependent system? What was that? You remember what that was?
System.
That's right. It would be a consistent system because we have precisely one ordered pair solution to this system. All right, one solution is called a consistent system. All right. Okay, any questions how we solve that system using the graphing method there? Okay. You can see why graphing paper is very important here, because if you don't use graphing paper, your tick marks are not going to be evenly spaced. And if your tick marks are not evenly spaced, you're going to be hard pressed to read off accurately this point of intersection. Okay, so it's very important that you use graphing paper for precision here. All right. Okay. All right, let's try another one. So we'll try to solve this one by graphing. And the system is going to be x plus 2y equals 8. And the other equation is 2x minus 3y is equal to 2. Okay. And to solve this system by using the graphing method, we have to take it upon ourselves to graph both of these linear equations. We got to graph this one. And then we're going to have to turn around and graph the other equation. Now, graphing this first equation here, we could, again, make use of the XY-intercept method if you want to. This one here doesn't look like you're going to get a nice y-intercept, because you would get negative 2/3 for the y-intercept. That's going to be kind of, cumbersome to plot. So I might use a different method to graph this linear equation. But this one here, I will utilize, again, the XY-intercept method. So to find the x-intercept, we set y equal to 0. Replace the y variable with the 0, and our equation is x plus 2 times 0 equals 8. So x is equal to 8. And hence we have 8, 0 as being our x-intercept. Our y-intercept is found by letting what? X be 0 always. So we're going to take 0 and we're going to substitute it in for the x variable. And our equation becomes 0 plus 2y is equal to 8, where 2y is 8. And then we divide both sides by 2. This would imply then that we get y is equal to 4. 8 divided by 2 is 4. So my y-intercept is the ordered pair of 0, 4. So we successfully found the x-intercept and the y-intercept for the first equation in that system. Now we can just plot those points in the xy plane. So we take a piece of graphing paper. And, here's my graphing paper, and I'm going to graph the first linear equation in the plane by plotting the x-intercept, which is 0, 8. So 1, 2, 3, 4, 5, 6. Oops! Wow, we don't have 8 available, do we? Doesn't look like we have 8 available. We got the y-intercept, which is 0, 4, though. 1, 2, 3, 4. All right, so that's my y-intercept. Since my x-intercept is going to be off the page here, what I'm going to do is I'm going to plot my y-intercept, which is 0, 4. And then I'm going to get this equation in the slope-intercept form by solving it for y. So how do I solve for y here? How do I solve this equation for y to get it from standard into slope-intercept form? What do we have to do here? Solve for y. How do I move a 1x over to the right side of my equation?
Subtract the x.
Let's minus off 1x from both sides. 1x's drop out on the left, leaving you 2y. I'm going to spin these terms around, negative 1x plus 8. Divide both sides by 2 now, and we will have solved for y. So therefore, y is equal to negative 1/2 x plus 4. So it does look like our y-intercept is 4. We determined that over here. And our slope is -1/2. So it looks like our slope is -1/2 or 1/-2. And our y-intercept here is indeed 4. Well, knowing my slope is -1/2 and my y-intercept being 4, I can plot more points on this line here. And so what I'm going to do is I got my graph here. I plotted the y-intercept of 4. And now I can use the slope being -1/2 to plot more points on this line. So if I view the slope as being -1/2, that means I have to go down 1 unit and 2 to the right. And I can plot another point. I could do that again, down 1 unit, 2 to the right, plot a point. Down 1 unit, 2 to the right, plot a point. Or I could have gone up 1 unit and to the left 2 units, 1/-2. Up 1 unit, 2 to the left. At any rate, we now take a ruler and put a line through these points, and we have the graph of that first equation in that system. So therefore, I put a line right through these points. And I have successfully graphed x plus 2y = 8. That would be its graph. So that's the graph of our first equation, x plus 2y = 8. Now we need to graph the second equation. This second equation here, we need to graph. And to do that, I'm going to get this equation in the slope-intercept form. So how would I solve this equation for y? How do I solve this for y? First, we got to move this 2x over to the right by minusing it from both sides. 2x's drop out on the left, leaving you with -3y. I'm going to spin these terms around and call it -2x plus 2. Now I'm going to have to divide both sides of my equation by a -3. This reduces down to y. A -2 over a -3 is as good as a positive 2/3. All right. Okay. So what we got going on, ladies and gentlemen, with this particular linear equation is we have put it in the slope-intercept form. So we know the slope of the line is positive 2/3. The y-intercept is really messy to plot, -2/3. Because the y-intercept is really messy to plot, I would be tempted to maybe find like the x-intercept here. And I could find the x-intercept by letting y be 0. I can see my x-intercept is going to be a nice number. So finding the x-intercept, we set y = 0, take 0, substitute in for the y variable. The equation becomes 2x minus 3 times 0 is equal to 2. This is gone to 0. So 2x = 2. Divide both sides by 2, and we get x is what? Positive 1. So it looks like my x-intercept is going to be 1, 0. All right, so now we know our x-intercept is 1, 0. We know the slope is 2/3. That should afford me the opportunity to plot any number of other points on this line. So I'm going to plot the x-intercept 1, 0, and then use the slope to plot more points on this line. So 1, 0 is right here. And now using the fact that the slope is 2/3, I can go up 2 units and then 3 to the right. 1, so up 2 from my x-intercept, and then 3 to the right. 1, 2, 3. I could do that again, up 2, 3 to the right. 1, 2, and I'll bet dollars to donuts, we got a point right about there. Or I could have viewed my slope as being -2 over -3. Which is to say I could have started my x-intercept and gone down 2 units and then 3 to the left. So down -2 and then to the left -3. 1, 2, 3. There's another point on my line. Down -2, 3 to the left, -1, -2, -3. Take a ruler, put a line through these points, and we have the graph of the second equation in that system. That is the graph of the second equation, which is 2x minus 3y equals 2. All right, ladies and gentlemen, now that we graphed both these equations in this system, does it appear that this system has a solution? And if so, what is it? Does that system have a solution?
Yes, it's 4, 2.
Okay, so it's our point of intersection here. And the ordered pair address of that point is 1, 2, 3, 4, 1, 2. So it looks like 4, 2 would be the solution to that system. And that's the only solution of this system of two linear equations and two unknowns. So 4, 2 is the only solution. So it appears that this system has precisely one ordered pair solution. So this would be an example of a what? Of a consistent system, correct? Consistent. Make sense there? That's a consistent system because we have precisely one ordered pair solution. Does that make sense, that problem there? We're solving these systems by graphing. Okay. So we got that one. Okay, we can try another one then. Any questions about this problem here? So when you're given two linear equations in a system, the way you choose to graph it, I really don't frankly care what method you choose to graph the equation. We just have to get it graphed accurately, okay? Whether you want to use a table method, whether you want to try to find X or Y intercepts to graph it. Yeah, maybe you want to get the equation in a slope intercept form and then graph it from the slope intercept form, knowing the slope and the Y intercept. That's another way. Okay, whatever way you choose, but we have to get them accurately graphed though. That is important. All right, let's try another one here. Let's solve by graphing. And my system is going to be y is equal to 2x minus 3. And the second equation is x equal to 3. So that's the system that we're going to try to solve via graphing, ladies and gentlemen. And we're trying to solve this system by graphing. As the name suggests, we're going to have to graph two linear equations. We're going to have to graph, first of all, y equals 2x minus 3. And then we're going to have to graph x equals 3. What's the nice thing about this first equation? What's nice about it?
It's in slope-intercept form.
It's in slope-intercept form, isn't it? So being in slope-intercept form, what two pieces of information can I deduce for the graph of that linear equation?
The slope and the y-intercept.
Yeah, so the y-intercept is -3, correct? And what's the slope?
2 over
2/1. All right, so here we go, ladies and gentlemen. What I'm going to do to graph that first equation in that system, y equals 2x minus 3. I know the slope is 2 or 2/1. I know the y-intercept is -3. That should be more than enough information to graph this linear equation. So first we'll plot the y-intercept, which is 0, -3. So 0, -3, -1, 2, 3 is going to be right here on the y-axis. That's the y-intercept. But we know the slope is 2/1. So if I start at my y-intercept, if I go up 2 positive units and 1 positive unit to the right, I should be able to plot another point. I can do this again. Up 2, 1 to the right, plot a point. Up 2, 1 to the right, plot a point. Up 2, 1 to the right, plot a point. Up 2, 1 to the right, plot a point. Do you agree? All those points are collinear. Or if you don't like going up 2/1, you could just as well go down 2 units and to the left -1 unit. So I could have went down 2 units, -1, -2, now to the left -1. Down 2 units, to the left -1. Either way, whether you go up 2 to the right 1 or down 2 to the left 1, doesn't matter. You'll still be plotting points on the same line. Take a ruler put a line through these points, and you have the graph of that first equation in that system of two linear equations and two unknowns. So this is the graph of y equals 2x minus 3. Now we'll try to graph the second equation. What would be the graph of x equals 3? Anybody know what kind of graph that's going to render? X equals 3.
Is it horizontal? Like a vertical line?
Okay, that's going to be not a horizontal line. It'll be what? A vertical line. And it will go through the x-axis where? It's going to be a vertical line that goes to the x-axis at 3. So take a ruler, put a vertical line right through x equals 3. Ladies and gentlemen, you have the graph of that second linear equation in a system. The graph of x equals 3 is that vertical line. Where do these lines intersect? They intersect right here. So what is that ordered pair solution? Can you read off its coordinates?
3.
3, 3. All right, so it looks like the ordered pair solution to this system would be the ordered pair 3, 3. So there we have it. It appears that 3, 3 is the only ordered pair solution, correct? It's the only ordered pair solution, 3, 3. That one makes sense there. And you can see that 3, 3 obviously satisfies the second equation because the x coordinate x is 3. X is 3. 3 equals 3. And it obviously satisfies the first equation. 2 times 3 is 6 minus 3 gives you y is 3, correct? So 3, 3 definitely is a solution to that system of two linear equations and two unknowns there. All righty. So far, ladies and gentlemen, all of our systems of two linear equations and two unknowns have been what kind of systems? They have been consistent. What about those two other scenarios? What about a system that's inconsistent, that has no solution? Or what about a system that has an infinite number of solutions? We haven't seen one like that before. We'll try to demonstrate one of each of those next. Okay. Any questions how we solve the system via graphing method? Okay. Well, let's try this one now. So we're gonna solve by graphing. First equation is y equals x minus 2, and the second equation in this system is y equals x plus 1. They want us to solve this system by graphing. First of all, we're going to have to graph the first linear equation, y equals x minus 2. And then we're going to have to graph the second equation, y equals x plus 1. We're lucky because both these equations are in what form? They're both in slope-intercept form. So what's the slope of this first line here? This first equation? Slope is 1. What's the y-intercept? What's the y-intercept of this equation?
-2.
-2. That should be enough information to graph that. Do you agree? Y-intercept of -2 is slope of 1. So we take our graphing paper here. What was that? Take a piece of graphing paper. And graphing the first equation, our y-intercept is -2. So -1, -2, there's your y-intercept. And your slope is +1, which means 1 over what? 1? So I start at my y-intercept, I go up one positive unit and then one positive unit to the right, plot a point. Do this again, up one unit, positive, up one positive unit to the right. Do that again, up one to the right one, plot a point, up one to the right one, plot a point, up one to the right one, plot a point, up one to the right one, plot a point. You go on forever. Or the slope could be interpreted as -1/-1, same thing. Could have started at my y-intercept of -2 and I could have gone down one unit, down -1 and to the left -1, plot point, down one to the left -1, down one to the left -1, down one to the left -1. Take a ruler, put a line through those points, and you have the graph of that first linear equation. So that is the graph of y equal to x plus 1. Do we understand how we graph that first linear equation? Y equals x minus 2. I'm sorry, this is the graph of y equals x minus 2. All right. Now we got to graph the other one, which is y equals x plus 1. What's the slope of the second linear equation?
The same.
Notice the slope of the second linear equation is also 1 or 1/1. And the y-intercept is what? Positive 1. So graphing the second linear equation, we know the y-intercept is positive 1 up here. And we know its slope is 1/1. So that means starting at the y-intercept, if I go up 1 and to the right 1, I can plot a point, another point on the line. Up 1 to the right 1, plot another point, up 1 to the right 1, plot another point, up 1 to the right 1, plot another point, etc., etc. Or we could go down -1 to the left -1, plot a point, down 1 to the left 1, plot point, down 1, left 1, plot point, down 1, left 1, plot point. Take a ruler, put a line through these points, and you have the graph of the second linear equation in that system. So that line is the graph of the other equation, which is to say y equals x plus 1. Ladies and gentlemen, do these lines intersect anywhere? Are those lines going to intersect? Do they share a common point? No. So the answer is, to this system, there would be what? No solution. There's no solution to the system. There is no ordered pair or ordered pair that satisfies both equations simultaneously. We call this a what? Inconsistent system. Inconsistent. Okay. Do we understand why that system has no solution? Because those are parallel lines, correct? Parallel lines have what? Equal slopes. Do they not? They both have the same slopes, and that's why they're parallel lines. They're not the same line because the y-intercepts are different, but the slopes are the same, and that's why they're unique parallel lines, two unique parallel lines. All right, so that's an example when a system has no solution. Now, there's only one other type I need to expose you to. That is a system that has an infinite number of ordered pair solutions. What kind of graphs would those have to look like if there's an infinite number of points of intersection? Maybe we better look at one. All right, so we will try to do one. We will try to solve this system by graphing. The first equation of which is 2x plus y equals 4. We'll try to graph that equation. And the second equation in this system is going to be 4x plus 2y equals 8. So we have a system of two linear equations and two unknowns. We're going to try to solve this system by graphing. And so that means we're going to have to graph both these linear equations. To graph the first one here, ladies and gentlemen, I think the XY intercept method will be the way to go. So to find the x-intercept, we let y be 0, take 0, substitute it in for the y variable. Your equation becomes 2x plus y, 2x plus 0 is equal to 4. 2x equals 4, divide by 2, and x turns out to be 2. So my x-intercept is 2, 0. To find the y-intercept of the first equation, we let x be 0, take 0, substitute in for the x variable, and then solve the equation for y. So we have 2 times 0 plus y equals 4. 2 times 0 is 0, that's gone, so y is equal to 4. So my y-intercept of the first equation is 0, 4. Take a piece of graphing paper now and let's plot the x and y-intercept. And let's see what the graph of that first equation would be. So plotting the x-intercept, which is a 2, 0, 1, 2. And the y-intercept is 0, 4, 1, 2, 3, 4. Taking a ruler now, and putting a line through these points. We have the graph of that first equation in that system. This is the graph of 2x plus y equals 4. Questions how we graph this first equation in our system. To graph the second equation in our system, again, I will make use of the xy intercept method. To find an x-intercept, we let y be 0, take 0, substitute in for the y variable, and my equation becomes 4x plus 2 times 0 equals 8. 4x, 2 times 0 is 0, that's gone, so 4x equals 8. Solving for x, we divide both sides by 4. X is equal to 2. So my x-intercept for the second equation is 2, 0. Finding the y-intercept of my second equation, I let x be 0, take 0, substitute in for the x variable into the equation, and solve it for the variable y. So we got 4 times 0 plus 2y equals 8. 4 times 0 is 0, that's gone. We're left with 2y equals 8. And then later on, we have to divide both sides by what? 2. And so y would be equal to what? 4. So my y-intercept would be 0, 4. It's your y-intercept. Now that we know our x and y-intercept, we can plot those points and then graph the second linear equation in this system of 2 equations and 2 unknowns. Does anybody recognize something interesting here?
0, 4.
Okay, what strikes us as being interesting with the x and y intercepts of the first equation and the second equation, ladies and gentlemen? What do you notice?
They're
0.
the same order pair.
They're the same. Notice the x and y intercepts of the first equation are precisely the same x and y intercepts for the second equation. So if I plot the x and y intercepts for the second equation and graph it, ladies and gentlemen, the graph is going to be the same line. So these 2 equations generate the same graph. They're both the same. So this line is the graph of not only 2x plus y equals 4, but it's also the graph of 4x plus 2y equal to 8. Everybody see that there? So ladies and gentlemen, how many points of intersection are there between this line and itself? How many points of intersection are there between a line and itself?
Would it be unlimited?
An infinite number, exactly. And that's why there's an infinite or infinite number of points of intersection. And because there's an infinite number of points of intersection, we say that this system, ladies and gentlemen, right here, this system of 2 linear equations and 2 unknowns has an infinite number of ordered pair solutions. Infinite number of solutions. We call this a dependent system. So when the graphs of both your linear equations and your system produce the same graph, the same line, then that system has an infinite number of points of intersection. Any point that lies on these lines is a solution to the entire system. And you can obviously see there's an infinite number of points that lie on this line. Okay. Sometimes we call this a dependent system because, ladies and gentlemen, if you take the first equation and multiply both sides by 2, do you agree that you generate the second equation? Do you agree the second equation is a what? Multiple of 2 of the first equation? If you multiply this first equation by 2, you would literally what? Generate the second equation. That's why we call this a dependent system, because these equations depend upon one another. They're really one and the same. They're equivalent equations. That's why they give us equivalent graphs. Okay. All right, you guys ready for one now? Classwork, ladies and gentlemen. All right, I want you to try to solve this system by graphing. Do we all have graphing paper out there or not? We'll call this classwork 1. Number 1, I want you to solve this system of 2 linear equations and 2 unknowns by graphing. That's the first one. Problem number 2, I want you to solve this system of 2 linear equations and 2 unknowns by graphing. There you go, ladies. I'm going to solve that system by graphing. Okay, you got 2 problems. See if you can solve them by graphing. Please use graphing paper. Very important. All right, anybody get the solution to number one here? Number one. Anybody get the solution for number one?
I got -1, 2.
All right, -1, 2. Anybody else?
Oh, 5.
Anybody else get -1, 2?
I did.
Okay, you did? All right. All right, so these should be the lines, what they look like for problem number one, when you graph those two linear equations. Your graph should look like this, okay? So that would be the solution to the system, -1, 2. Anybody get the second one solved?
You start to. Oh,
I think
Number two,
-3, 2.
-3, 2. Okay, did anybody else get -3, 2? -3, 2?
Yes.
Okay, so when you graph those two equations in the second system, you get -3, 2. All right, and again, I don't really care how you graph these lines. I mean, whether you want to, generate some ordered pairs by using a table, find the x and or y intercepts, or you can put the equation in slope intercept form and graph it that way. I'll leave that up to you, but the bottom line is we got to be able to graph these things correctly in order to determine the solutions to these systems. Okay. All right, -1, 2 and -3, 2. Okay, ladies and gentlemen, that will be classwork number one. The only other thing that I want to look at is how to apply these to the real world, these systems of two linear equations and two unknowns. And to do that, we're going to go to our textbook. I want to show you something here. That's assuming technology allows me to do that. All right, so I want to go to page 275. Whoops. Hold on a second here. So I want to graph 275. All right, problem number 42 here. This involves a truck rental. It says you need to rent a moving truck for 2 days. Ryder moving truck charges $50 per day and 50 cents per mile. You Move Trucks, on the other hand, charges $45 per day and 75 cents per mile. The following figure represents the cost of renting each of the trucks for 2 days. So as I'm gonna notice, the horizontal axis is our mileage axis, the number of miles we put on the moving trucks, and the vertical axis is the total cost of having rented that truck and putting the miles on it. Notice the graph of the You Move truck that's rented is the blue line. The graph of the Ryder moving truck is the red line. Okay. And then they're going to ask us some questions here. For problem 42A, it says from the figure, how many miles would the trucks cost? How many miles would we have to drive, ladies and gentlemen, both trucks for the two different moving companies in order for the trucks to cost the same? You would say, how many miles would that be? In order for the cost of both these trucks to be equivalent, the same, how many miles would we have to drive each truck?
40.
How many?
40 miles.
40 miles, exactly. If we drive each truck 40 miles, ladies and gentlemen, notice the cost will be identically equivalent, $120. So if we put 40 miles on the You Move truck and 40 miles on the Ryder truck, both rental plans will yield an equivalent cost of $120. For part B, which company will give you a better deal if you drive less than 30 miles? If we drive less than 30 miles, ladies and gentlemen, should we go with the U-Move truck or the Ryder truck? If we plan on putting less than 30 miles on the truck,
You move.
the U-Move rental will be cheaper. Do you agree? Because for X less than or equal to 30 miles, the blue line is below the red line, which means the cost of the U-Move rental is less than the cost of the Ryder rental. So you would go with the U-Move rental if you plan to only put 30 miles or less on the vehicle. Ryder would cost you more in that case than the U-Move truck. C, which company will give you a better deal if you drive more than 60 miles? If you plan on driving more than 60 miles, what truck would be the more cost-effective rental?
Ryder.
Ryder, because notice for X equal to or greater than 60 miles, the red line is below the graph of the blue line, which means the cost of the Ryder rental will be less than the cost of the U-Move rental if we plan to put 60 or more miles on the truck. You definitely want to go with a Ryder in that case. Does this problem make sense here, ladies and gentlemen? All right. And notice that these two lines came from two different linear equations. I have a question for you. Which linear equation would have, or which line would have the greater slope, the blue or the red line? Which line has the greater slope, blue or red?
Blue.
Which one?
Blue.
The blue. The
I
blue
said
line,
blue.
yeah, the blue line has the greater slope. That's the U-Move rental. And there's no surprise why it has the greater slope, because the U-Move rental charges you 75 cents per mile, whereas the Ryder, the red line slope, is only 50 cents per mile. So notice the U-Move blue line has a slope that is 25 cents per mile greater than the slope of the red line, the Ryder rental. But notice the Ryder rental charges you more up front, ladies and gentlemen, $50 per day, as opposed to the U-Move rental only charges you $45 per day. So there's goods and bads between both rentals. And the one we would choose would really, in large part, depend upon how many miles we plan on putting on the vehicle. Do you agree? That's what would dictate our decision. All right. So, ladies and gentlemen, for classwork number 2, I want you to do problem number 41 here. So there's problem 41. I want you to, looking at that, I want you to answer those questions for 41, A, B, and C. We'll call this our last classwork for the day. We'll call this classwork number 2. All right, so I'll give you time to work on number 41, A, B, C. Go ahead and take care of that. All right, ladies and gentlemen, it says for problem 41, Jane is deciding between two sales positions. She can work for Marcy's and receive $8 per hour, or she can work for Gigi's, where she earns $6 per hour, but also receives a $50 commission per week. The two lines in the following figure represent the money Jane will make for working at each of the jobs, Gigi's versus Marcy's. Question A, from the figure, how many hours would Jane have to work to earn the same amount at each of the positions? Anybody get an answer for that question?
25.
25 hours. If she works 25 hours for both companies, she will receive the same amount of money of $200. For part B, if Jane expects to work less than 20 hours a week, which job should she choose to go with as being the one that provides more money? Less than 20 hours.
GG's.
Gigi's, okay. If you're going to work less than 20 hours, it would be wise to go with the Gigi's job as opposed to Marcy's because it will pay you more money. The red line being above the blue line for X less than or equal to 20. Finally, part C, if Jane expects to work more than 30 hours a week, which job should she opt for?
Marcy's.
Marcy's job will then pay more if you plan to work 30 hours or more. You want to go with Marcy's because it will, afford you more of an income there. Okay. All right. So today, what we did is we concentrated on what's called the graphing method for solving these systems of two linear equations and two unknowns. On Wednesday, we will wrap up chapter 4. Chapter 4 only has 3 sections in it, so we're going to wrap up chapter 4 on Wednesday by looking at two algebraic techniques for solving systems of two equations and two unknowns. The addition or elimination method, and then the substitution method. Okay. Why do you think you would even want to have an algebraic or numerical way of solving these systems? Why not just solve them all by graphing? Well, ladies and gentlemen, let me give you an idea as to why it's important to be able to solve these systems using a numerical technique. All right. Suppose we had 2 lines graphed, and suppose that they intersected. Let's say they intersected right about here. Do you agree it would be very difficult to read off that point of intersection? Everybody see that there?
Yeah.
That would be very, very difficult to accurately read off the X and Y coordinate ordered pair address of that point, because these lines do not intersect at the intersection of vertical and horizontal tick marks. Who knows? Maybe the solution is this system is a messy ordered pair solution of 0.157 for the X coordinate, and maybe the Y coordinate is like 1.678. Do you agree, ladies and gentlemen? There's no way we're ever going to be able to read off this ordered pair from the graph here. There's no way. It's too difficult to read off these decimal coordinates here. And for that reason, the graphing method would fail for this type of system. It would fail miserably. And for that reason, we need to have an algebraic or numerical way of solving a system like this that has messy ordered pair solutions. We should go with either the addition method or the substitution method. And we'll look at these techniques on Wednesday, okay? The addition or the substitution method for solving systems of two linear equations in two unknowns. All right, so this would probably be a good place to stop here, ladies and gentlemen. We had 2 classworks, so you can get those into me. I will also make available the chapter 4 quiz after the Wednesday session, and also the chapter 3 and 4 exam will be made available, and I will indicate the due dates for those 2 things there through an email, okay? And also what you should turn in for your chapter 3 and 4 textbook homework. I will specify with an email. All righty. Okay, so if there are no other questions, then I'm gonna let you go for today. And hopefully I'll see you on Wednesday. All righty. All right, have a good evening.